Wow, a fraction. A fraction is just a part of a whole, right? And we have different ways of writing fractions. We have improper fractions, mixed fractions, blah 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 blah. But at the end of the day, it's just talking about one thing being broken up into parts. So the best way to represent it, which I'm sure you've seen before, is with pizza. Usually a circular pizza because it's easy to break up circles into fractions. So if you took a pizza,
Unless it's like quarters and it's easier. Then it's easier if it's square.
yeah, and squares, some people are really good at breaking squares up into fractions. I'm just personally not. Circles are much easier for me. So if you look at these three pictures of pizza, they're all broken up into fractions. Okay, and then we can compare the fractions to the pizza, so you can go back and forth. If you look at the first pizza, I think anyone there could look at that and be like, that's a half of a pizza, right? The way we represent 1/2 in math would be 1/2. 1 represents the amount you have. 2 represents how many pieces you've broken it up into. So we had one entire pizza, and we broke it up into 2 halves. There's this half, and there's this half. That's why the bottom number is 2. We broke it into 2 pieces. And you only have one of those 2 pieces. Hence why it's 1/2. If you look at the second pizza, it's been broken up into 4 sections. I'm going to use red, not right. 4 sections. 1, 2, 3, 4. That's why the bottom number is 4. And the number of pieces you have would go on the top. In this case, there's only 1 piece you have. The third pizza has been broken up into 8ths. Like this. Right? 8ths. 1, 2, 3, 4, 5, 6, 7, 8. So 8 would go on the bottom. And you have 3 pieces. 1, 2, 3. That's why 3 went on the top. That's all fractions are representing. How many pieces of a whole that you have. Awesome. You've seen that before? You've seen circles, squares, triangles, whatever. They break them up into different quadrants or amounts. And hopefully you just remember, okay, the bottom's how many I'm broken up into. The top is how many I have. So if I said you had something crazy like 97 over 102, that just means that you have something that's been broken up into 102 little things, and you have 97 of them. It'd be sweet if you had a pizza broken into 102 pieces. It'd be a little bite-sized pizzas or something. I don't know. Equivalent fractions. So equivalent fractions are usually the thing that mess people up because 1/2 might not always be represented as 1/2. Right? It can be represented in different ways. For instance, you have 3 different pizza pictures here, okay, which have been broken up into different amounts of slices. So if you look at the first one, it's been broken up into 2 slices. 1, 2. If you look at the second one, it's been broken up into 4. 1, 2, 3, 4. And if you look at the third one, it's been broken up into 8s. They even did the lines for you this time, which is nice. 1, 2, 3, 4, 5, 6, 7, 8. And despite the pizza being broken up into all these different slices, how much pizza do you have in all 3 of those pictures? You have half a pizza in all those pictures, right? Look at them. I have half the pizza, I have half the pizza, I have half the pizza. The number of slices it was broken up into changed, but the total amount of pizza you had in each one actually didn't change. It always ended up as being half the pizza. That's called equivalent fractions. So mathematically, we represented these all differently. The things I'm circling in blue. The first one was you had 1 piece out of 2. The second one was you had 2 pieces out of 4. The third one is you had 4 pieces out of 8, but they all actually still equal half of a pizza. You have the same total amount. Those are called equivalent fractions. It's the same idea as if you said somebody told you they have 2 quarters, right, money-wise, or they have half of a dollar. Right? It's the same thing. Both people have 50 cents. Just one's talking about having quarters and one's talking about have half of a dollar. You're just having different reference for how you've broken up money.
There was a 50-cent coin.
Long time ago. I used to have one of those. I think my kid has one.
Yeah, when I was a kid, they did too. They had them in like 2000.
Boom! Mind blown.
Yeah, my mind is.
Wait, you said you
I think so. I think I saw it.
I don't think I've ever seen 50 cents.
Yeah, I think he got it from his grandma. I think she gave it to him. It's like a big silver coin. It's like it's almost as big as a loonie. It's pretty big. It's like almost as big as a loonie. It's like a big coin. Yes, sir.
It's about points.
Yeah.
My grandpa has like 3, like 20, like
Write things as equivalent fractions. Like we can make fractions have a bigger bottom number. We can make fractions have a smaller bottom number, and they're all still the same thing. They're all equivalents. Below, we have a couple pictures of equivalent fractions and how we got those equivalent fractions. So if you look at the ones in blue on my page, the one that starts with 1/2, this guy right here, every one of those fractions equals the same thing. And what you'll notice is that to get from one fraction to another, they're multiplying the top and the bottom number by the same amount. So for instance, 1/2 is the same thing as 2/4. All you had to do is take the top number, multiply by 2, and it would give you a new top number. And you can keep doing that. So if I had 2/4, if I multiplied by 2, it gives me 4. If I multiply the bottom by 2, it gives me 8. And those are equivalent fractions because I'm doing the same thing to the top number and to the bottom number. It doesn't just have to be by 2. You could multiply by anything. So if you look at the second one, they started with 3/4. They created an equivalent fraction first by multiplying by 2 to get 6. Multiply by 2 to get 8. And then they showed you could actually multiply by something else. They multiplied by 3 this time to get 24. Multiplied by 3 to get 18. But they're still equivalent fractions as long as what you do to the top number, you do to the bottom number. And that kind of comes a phrase that hopefully you've heard before is what you do to the bottom, you do to the top. Right? It's a balancing act. In math, a lot of the algebra, a lot of the stuff we do is some sort of balancing act. So if you're doing something to a number, whatever you do to the top, you have to do to the bottom to balance everything out. As we get further into algebra, we'll talk about that as well. You kind of saw it with BEDMAS a little bit. You had to do things in a certain way to balance everything out. We're going to talk about the top number of a fraction. Top number of a fraction. And the bottom number of a fraction. Because as we do fractions, I'll often refer to them as two different things. I'll use both words in the same sentence. So you hear the common language that's easy for you to recognize, and then the mathematical language so that you actually know what the term is. The top number on a fraction is called what? Yeah, it's the numerator. Awesome. The top number of a fraction is the numerator. I will typically say you have to do that to the top number or you have to do it to the numerator. I'll say both so that you kind of keep linking together numerator and top number. Yeah. Yeah, it's the denominator. Just terminology, right? It's stuff you've heard before, but you probably just forgot. I review it in every single grade. Right, all the way up to grade 12, where it's just like, remember the top number is called the numerator, bottom number is called the denominator. Just because it's easy to forget. Cool. Today is going to be all about calculating equivalent fractions and different ways of doing it. Example 1. We're going to create 3 equivalent fractions for the following. They're all 2/5. So we're going to create 3 different equivalent fractions. The way we create equivalent fractions is by multiplying the top and the bottom by the same thing. So for instance, I could change 2 over 5 by multiplying the top by 2 and multiplying the bottom by 2. This would create the number 4 on the top, 10 on the bottom. And that would be an equivalent fraction. If you wanted, you could just write it as 4 over 10, a little smaller. Yeah. Would 10 over 25 work? It would. So Joey gave us another one. He's saying if you took the top number and you multiplied it by 5, and as long as you did the same thing to the bottom number, multiplied it by 5, you would create an equivalent fraction. The top is 2 times 5, that's 10. Divided by the bottom, that's 5 times 5, that's 25. 10 over 25 would be an equivalent fraction. As long as what you do to the bottom, you do to the top.
Wait,
Yes, sir.
okay,
Merrick.
Would 20 over 50 work? And your times are going to both by 10.
Yeah, so if you took the third one, and you multiplied the top by 10 and the bottom by 10, the top number would become 20 because 2 times 10 is 20. The bottom number would become 50. Those are all equivalent fractions. They're all the same amount. It's just something's being broken up into different pieces. They all represent 2 out of 5 pieces of pizza. If you had a piece of pizza and cut it up into 5s. Yeah, it's in the top drawer. It's just a little tiny guy. Cool. Looking at rational expressions. Talk about grade 11 problems right now. Talking about fractions, which we have here. They could give you equivalent fractions and give you a missing piece. And you would have to figure out what that missing piece is. So for instance, if you look at A, they're telling you that 1 over 3 will be equivalent to or equal to 18 divided by something. The way to figure out what that bottom number would be to figure out how these two things were related using multiplication or division. So how could I make 1 become 18? That's what you got to ask yourself. Prax. Yeah, multiply it by 18. To get from 1 to 18, I multiplied by 18. So if you want an equivalent fraction, you need to multiply the bottom number by 18. Again, multiplication is just skip counting. So you need to skip count by 18 3 times. That's a hard one to skip count by. You could always put 3 times 18 in your calculator. That would work as well. Pardon? 18 times 3? 18 times 2 would be 36. Times another 2 would be 54. So it would be 54 on the bottom. You were close. So 54 is the missing number there. Yeah, turn. Yes, sir. They could do the same thing, but take away the top, and you could have to try to find the top number. But the same idea is going to apply. You're going to compare the bottoms, and you're going to ask yourself, how did I make 4 become 24? If you're not sure, if you're like, 4 times something, and maybe you just don't remember your multiplication table that well, you're like, I'm not sure what it is. What you could do is take the second number, in our case 24, and you could divide it by 4. And that would tell you how much you had to have multiplied by. It kind of goes off what we talked about on Tuesday. You can rewrite multiplication as division. You can rewrite division as multiplication, right, to help find each other. In this case, 4 times 6 gives me 24. That means on the top number, I need to multiply by 6. 3 times 6, if I didn't have a calculator, means count by 6 3 times. 6, 12, 18. The top number is 18.
18?
Yes, sir.
Sorry, I can't hear you.
Yeah, maybe. I wonder why. So if you look at C and D, I want you to try both those on your own. See if you can fill in the missing blanks. C and D are set up a little bit differently. Okay, they took the missing number and put it in the first fraction. So there's different ways you could tackle this. I'm going to show you different methods. Okay, the first way would be exactly what we just talked about. You could look at 6 and say, how did 6 become 36? And you'd be like, oh, I times by 6. That makes sense. That's one way to do it. Okay, but then trying to figure out what number multiplied by 6 gives you 45 could be kind of challenging. And that's not an easy thing to figure out, mainly because it's a decimal. It's not like a perfect value. So you could work yourselves backwards as well, which is what I believe it was Damon had just said. So instead of going from the left to the right, you could understand that equivalent fractions are equal both directions. That means instead of multiplying, I could ask myself, what number do I divide by to get an equivalent fraction? So 6 divided by 6 would give me 6 on the first one. That means I have to ask myself, what happens when I take 45 and divide it by 6? And what do you get, David? Or do you have a question or do you have an answer?
Okay, 16 or 14?
No.
7.5.
It's 7.5?
And then can I go to 1?
Yes, you may. So if you were to work backwards, right, divide the top, divide the bottom, it works the exact same way. So that gives us a new rule. If you want an equivalent fraction, you could multiply top and bottom, or you could divide top and bottom to get an equivalent fraction. Right? They work the same way. So if you look at D, if I asked myself, how do 16 and 32 relate? I could look at it as, well, 16 times by 2 to become 32, or I could look at it as 32 divided by 2 to become 16. Right? It's the same thing. You're just thinking opposite direction, so opposite operation. The opposite of multiplication would be division. That means you could ask yourself, what number times 2 would be 28? Or you could say, what happens when I take 28 and I divide it by 2? Either way, you should get an answer of 14. Again, that would work with multiplication. 14 times 2 does equal 28. As long as what you do to the bottom, you do to the top, you'll be good. Yes, sir.
I got a question.
Yeah.
So why do you grade forwards like all the way up?
It is creating a equivalent fraction, but it has a special term. It's called reducing a fraction. So when you're reducing a fraction, that means you're dividing. Another term, and the one you will actually hear, especially moving forward in high school, is you won't hear your teachers ever say, reduce that fraction. It's not going to happen. They're going to say, write that fraction in simplest form. Okay, that means write it in the smallest numbers possible. It's the same thing as saying reduce. I could tell you it's 1/2, or I could tell you it's 50/100ths, but 50/100 is a ridiculous way to describe half of something, right? 1/2 is way simpler to say and understand. So we will always reduce our fractions into simplest form. Moving forward in high school, that's what you'll do all the time. Every single answer will have to be in simplest form. So you'll reduce it, make it smaller numbers. The best way to do it is by dividing, in my opinion. So if you look, you got 3 fractions right there. You'll notice that they took 40/60, and the first thing they did was divide by 10, which is wonderful. That got you 4/6, which is an equivalent fraction, but it would not be the reduced fraction, and it would not be the simplest form fraction because it's not the smallest number you could get. You could reduce 4 and 6 even more, right? You could still divide them by another 2 to get 2/3. That would be my simplest form. Your goal is going to be to write things in the simplest form as you move on, especially at higher grades. Awesome. We're going to look at 24 over 1/8. We're going to try to reduce it. Okay. I'm going to do it in a lot of slow steps. That's okay, because I think that's how most people would see this. So if I look at 24 and 108, and my goal is to reduce it. Reduce means I want to divide the top and the bottom number by something that they can both be divided by. So what's a number I could divide 24 by, and I could divide 108 by?
18.
Yeah, think really small first. You're right, but think
Wait,
small.
yeah.
No, you're all right. Joey, what's a small number you can reduce by? 2. I could divide both the top and the bottom by 2. If I did that, my top number would be 12. My bottom number would be 54. And if you look at 12 and 54, and you ask yourself, could I reduce that further? Could I divide them again? The answer would be yes. What could I divide 12 by and 54 by? You could divide by 3. Or 2 again, right? Either or. So let's do 3 just to see what happens. So I'm going to divide both top and bottom by 3. That would give me 4 on the top. And on the bottom, it would give me... Why'd you have to pick such a hard number for me?
18.
Thank you. Brain is working in backwards. I'm like dividing by 2. I'm like 27. 27 divided by 3 is 9. 9 times 2. And I'm like working my way backwards.
I can't think without you.
If you look at 4 over 18, could it be reduced again? And the answer is yes. I could divide 4 by 4, correct, but I couldn't divide 18 by 4. It's a number I could divide both of them by, which would be 2. So I would divide the top and the bottom both by 2, and I'll finally get my simplest form, which is 2 over 9. That would be my simplest form. Definitely. Now, that's one way to do it. It's a little tedious and slow, right? Because we had to divide by 2, then we had to divide by 3, then we had to divide by 2. So there's multiple steps to it. You could reduce things faster. The way you reduce them faster is by taking the exact same question, 24 divided by 108, and trying to figure out if there's a bigger number you could divide them by. What could I divide by? 12. So if I took 24, divided it by 12, I get 2. If I took 108, divided by 12, I would get 9. And you notice that I get to my reduced form quicker. Both methods work. Typically, with harder numbers, so like the bigger they get, the more steps you'll have to do. Because it can be sometimes hard to tell what divides into something. With smaller numbers, it might be easier. You might be like, oh, those both divide by 4, and then you don't have to do 2 and then 2 again. Yeah. So, I mean, just the more you practice, the better you'll get. Try to divide by big numbers. Makes your life easier. That's my suggestion. Awesome. We have 4 right here. We're going to try to reduce these. I'm going to do them in 1 step, and then I'm going to let you try 2 on your own. You can do them in 2 steps. I'll do A and D for you. So if I look at A and I wanted to reduce that, if I want to do it quickly, I want to try to find the biggest number that could divide into both of those. To do that, it might help just to focus on one of the numbers. And I'm going to look at the number 20 because it's smaller. And I'm going to list all the things I could divide 20 by. I could divide by 2. I could divide by 4. I could divide by 5. I could divide by 10. and I could divide by 20. Those are all numbers that could divide into 20. And if you don't know what those are, just try it on your calculator, right? Like guess and check. Be like 20 divided by 2, enter. Oh, it worked. Awesome. 20 divided by 3, enter. Decimal, didn't work. 20 divided by 4, awesome, it worked. And you'll get eventually better at your multiplication tables, and you'll be able to pick out which ones are working, which ones don't work. Now that I have those list of things that can divide into 20, I'm going to try to find the biggest one that can divide into 36. 2 divides into 36. 4 divides into 36. 5 does not. 10 does not. 20 does not. The biggest one that divides in is 4. So the best way to do this question, or the quickest way, would be to divide the top and the bottom by 4. So that gives me 5 divided by 9. And I know I've done the question because 5 and 9 cannot divide by anything. Right? 5 can only be divided by 5. 9 can only be divided by 9. They don't have anything they can both divide by, or 3. But they don't have something they can both divide by. This process that we just did is called dividing by the greatest common factor. I don't know if you've ever heard that term before, but it's divided by the biggest number that divides into both things. That's what it means. Greatest, biggest. Common means they both have it. And factor means can divide into. Biggest number that can divide into both things. That's what that means. I'll do D with you. Yep. So if I looked at D, I have 72 and 96. If my goal is to divide by the greatest common factor, I want to divide by the biggest possible number that goes into 72 and 96. They could both divide by 2. I'm going to say can divide by. 72 can divide by 2. It can divide by 3. It can divide by 6. It can divide by, I don't think it can divide by 4. Did I miss 4? Yeah, I missed 4. By 4, by 6. It can't divide by 7. It can divide by 8. It can divide by 9. Can't divide by 10. Can't divide by 11. It can divide by 12. 12, 24, 36, 48, 67. Yep. It can divide by 13. No. Can divide by 14. No. 15. No. 16. Nope. 17. No. 18. Yes. 19. No. 20. No. 21. No. 22, no. 23, no. 24, no. All the way up to 36. 36 does. And then 72 does. I don't think I missed any.
It does divide.
Oh, I missed one.
72 does divide by
I missed one in the 20s.
24.
Yeah, no they don't. 96 doesn't.
24, 48, 72.
Yeah.
And then 36, and then 72.
They don't divide, but only 72 divides by 24. 96 doesn't.
Right, we're not on that part yet.
Divide by 24.
Hold up. We're not at that part yet. I mean, it does. It does, but we're not at that part yet. So,
It's 4.
yeah, it is. Yeah, it's a perfect number. Regardless, we're not at that point right now. All we're doing is we're trying to figure out the things that could divide into our smaller number. These are all the numbers that could divide into 72. That's also known as a factor of 72. Right? Things that can divide by, these are called factors. Factors. It's the numbers that can divide into 72. Your goal is to find the biggest one that also divides into 96, is also a factor of 96, and it is 24. $72 divided by 24 is 3. 96 divided by 24 is 4. So that thing reduces to be 3/4. I want you to try to reduce B and C. If you're reducing them and you can't find the biggest one, that's fine. Just get it to simplest form. Okay, so if we look at B first, you could try to find the biggest number that divides into both of those, or you could try to do it in chunks. Okay, so just as a reminder, I'm going to try to do it in simpler chunks because that might be easier for people. 54, I know, can divide by 2. 66, I know, can divide by 2. 54 divided by 2 is 27. 66 divided by 2 is 33. And then if I look at both of those numbers, I would ask myself, is there something that can divide into both of them? Have you guys seen the can divide by 3 trick? Like how to tell if something can divide by 3? Oh my goodness, it's the best thing.
6, 9. Yeah, you like add all the numbers. Like if it's 9 to 2, you go 9 plus 2.
Yeah.
Which equals 11. And 11 is
Exactly. So it's actually a pretty cool trick. So if you look at the number 27, I know 27 can divide by 3 because 2 plus 7 equals 9, and 9 can divide by 3. If you look at 33, 3 plus 3 equals 6. I can divide 6 by 3. That means 33 is divisible by 3. And that works for any number. So if you like pulled out some crazy number out of your hat and you were like 692, 133, and you're like, can that divide by 3? If you added all the numbers, 6 plus 9 plus 2 plus 1 plus 3 plus 3, it would equal, that's 6, 7, 8, 9, 18. That equals 24. 24 can divide by 3. That means this number can divide by 3. It's a pretty cool little trick. So if you add numbers, the digits of the number, and it can divide by 3, then the whole thing can divide by 3. That's actually a pretty sweet trick, eh? So 27 can divide by 3. 33 can divide by 3. That becomes 9/11. 9 and 11 don't share anything they can both divide by, so 9/11 is my simplest form. If you wanted, you could have divided both by 6. Yeah, and that would have been the faster way to do it, which would be 9/11 still. Try 54 divided by 6 again. Yeah. 66 can't divide by 9 though. Awesome. If we look at C, we have 30 and we have 75. The quick way to do it would be to divide both of these. I believe 15 works. $30 divided by 15 is 2. 75 divided by 15 is 15, 30, 45, 65. 70. Yeah. Two. Next week's a full week, yeah.
Well, we missed one.
Yeah. Awesome.
Yeah.
Whoa.
Whoa, that's a screen.
No, Rachel doesn't practicing that. You got a stupid science.
How about that?
There we go.
I know. I'd rather go
That's simplifying fractions. It's not bad.